Okay, so today I want to talk about continuity, and we've kind of danced around the notion of continuity for a while, and this is going to be our formal definition of continuity. Okay, it's going to be that if we take the limit as x approaches a of f at x, that's going to equal f at a. Okay, now we kind of know that for a few things that we've worked on. For example, when we have in those problems that you did for homework, as the limit as h goes to 0 of h, well, that's equal to 0. So h is continuous if h is a function. So f at x equals x is a similar kind of thing. So as x goes to any value, we get to that value. So this is what we're going to call continuous. And any definition that we have around, or any time we're trying to show something is continuous or not, this is the definition we're going to use. Okay, so then the nice part about this is that when we have continuous functions, we can evaluate the limit by just sticking in, just by plugging in a. Okay, so there is already an implication here that a is in the domain of f, right? Because if it's not, then it wouldn't be continuous, because certainly we can have a limit like all those things that you did for homework. It definitely had a value as h went to 0, but you just couldn't plug in 0 at the beginning because you have 0 over 0. So those functions that we did, that you calculated the limits, if you boil it down, were not continuous functions at that point. They weren't continuous at 0. But if we have a function whose domain includes a, we just plug in a, and we can see if it's continuous or not. Okay, so the three things that I'm implying here is that f at a is defined, so what I just said, a is in the domain of f, that the limit exists. Okay, it's possible that we have a value at f at a and that the limit doesn't exist. I'll show you a couple of cases where that's the case. And then the third thing is that, of course, that the limit equals the function evaluated at that. So really this statement, even though it looks like a single statement, is really implying three things. And when we look for continuity, we want to make sure that all of these three things exist. Or not exist, but are true. Okay, everybody up with me here? All right, so let's look at a couple functions here and look at some behavior. Now, if we look at this, okay, so here we're going to try and get to the limit as we go to a of f. We're trying to find the limit of f at x as x goes to a here. And so here we have this line, and of course you see it, as we get closer and closer to the value of a from the right, it gets closer and closer to that x, and from the left it does the same thing. And so here we could say here definitely that the limit exists because it's the same both ways, and the limit equals the value evaluated at a. So this is just kind of the thing I'm describing with a continuous function. Now let's look at this function. Okay, so we can say f at a is continuous, that first one. Now this next one, if we go from the left, here I'm going to be talking about point B. If I come from the left or I come from the right, I have two values that are equal, right? They both come to the point where that little hole is. But what's wrong with that is that that b is not in the domain of this function. In other words, f at b does not exist. That's what the hole says, is that there's a value that's missing. So we say that, or g, I guess is the function that I'm talking about here, that the function g is not continuous at point b. Okay, so you go along here and the value's missing. So it's not continuous. So if we look at point A now, we have the limit coming from the left and the limit coming from the right are two different values. So even though f at a exists right here, the limit does not exist. And so this function is not continuous either. And hopefully intuitively you can just see that these are not continuous. What you think about continuous is that it just keeps on going for every number, you get a new value, right? And so here we can see, okay, here's a discontinuity, here's a different kind of discontinuity, but they're both discontinuous at, or both of these points represent a discontinuity, both A and B. Everybody with me okay? So we say G is discontinuous at B, it's discontinuous at A. Okay, so let's look at a few functions and say, where are they discontinuous? Where is this one discontinuous? At x equals 1, right? Because when we graph that, we're going to get a graph that looks like f at x equals x plus 2, but that x minus 1 there is going to throw us a loop because it's going to be 0 over 0 when x equals 1. Okay, how about this? Now, what if I say here that when x equals 1, I have a point. Okay, where is that discontinuous now? Because now I have a function that is defined at x equals 1. Is it continuous now? Well, from both directions it'll approach the same value here, and then here is a value that we've defined, okay? But there's a problem with this, right? If we think about the graph of this thing now, it'll still look like x plus 2, but at 1 you would expect this value to be 3. So the limit of this function as x goes to 1 is actually 3, even though f at 1 is 0 by our definition. Okay, so if I were to draw a picture of this, my function would look like this, right? It would be a line with slope of 1, but at x equals 1, there's a discontinuity. So this is that function, the first function f at x. Now the second f at x here, I'm defining, when x equals 1, I'm defining my function here. So I'm going to plot that point as that. So it's discontinuous. We go along this line, and then all of a sudden the function makes a jump down to this value, and then if we move off the value, then it continues along its line. So this is discontinuous as well, because the limit as x equals 1, or excuse me, the limit as x goes to 1 is not the same as f at 1. Okay, what about here? Where is it discontinuous? At 0, right? Because it's not defined, because f at 0 does not exist. What is the limit of f at x as x goes to 0? What do you think? Now, we haven't talked about limits that equal infinity, but one of the things that you'll hear next Monday or Wednesday is that when you have something like this and the limit of f at x as x goes to 0, that this will go to infinity. All right, so we do have a limit, not really a value, but conceptually we say it increases without bound. Okay, so it's not like the limit is a value, it's more or less a concept. Okay, so, but the real reason why it's not continuous is because f at 0 is undefined. How about this? F at x equals the absolute value of x over x. Here, if we look at the right and the left-hand limits, we say, okay, as x goes to 0 from the positive side, okay, that's going to be 1, right? Because if we're always positive, the absolute value sign does nothing. But if we're negative, then this function is going to change the sign of the numerator, and so it's always going to equal -1. And so drawing a picture of this one, I'll do it on the same graph here. This one looks like this, right? And we don't have f at 0 defined, because that would be 0 over 0. Okay, so we have a jump there in our function, and so it's not continuous. The limit as we're coming from this direction and the limit as we're coming from this direction are not equal, so the limit does not exist. So this one fails really in two accounts. Number one, f at 0 does not exist. Number two is that the limit does not exist. Do I have any questions? Okay, so let's kind of categorize our discontinuities. There's three different kinds of discontinuities, and they have a name. This is what's called a removable discontinuity. It's removable in the sense that if I simplify this and I get just x plus 2, I'll remove that discontinuity. So here, what this is saying is that it's not continuous because we're missing a value, but it's easy to define this function now that says f at x equals this when x does not equal 1, and then assign the value f at 1 equals 3. So if I make it a function by assigning a value to it, I can make it continuous if I assign the right number. If I make that just any arbitrary number, it wouldn't be continuous. But if I said f at 1 equals 3, then I'd have a continuous function. Okay? So you call this a removable discontinuity, that we basically don't change the definition of the function, but either through a simplification or an addition of something, we make it, nothing else changes except that one point. And so we have that as a removable discontinuity. So then we have this kind of thing, which is 1 over x squared. Okay? So this we call as an infinite discontinuity. Yeah, from this side it goes to infinity, and from this side it goes to infinity. But infinity, there's no match here. There's no value at 0. I mean, the closer we get to 0 from either side, the larger the number we get. But we never get to a particular number, and so this is discontinuous. And so by our definition of discontinuity, we know that f at 0 does not exist, and so we call it discontinuous, but if we look at the graph of this, we know that the nature of this one is because it's an infinite discontinuity. And then the last one is the one that we had with this absolute value of x over x, where the function actually takes a step and it changes dramatically. This is what's called a jump discontinuity. And so oftentimes we'll be dealing with the jump discontinuities if we want to do things like find the area under the curve and things of that sort. We will just consider portions of this thing and adding them together rather than applying anything that we have, any theorem that we have that suggests that we have to have a continuous system before we operate on it. So we can operate with this in pieces, but we can't operate on it as a whole because it's discontinuous. Okay, so three kinds of discontinuities. Okay, so now we're going to get into a little bit of a refinement in our language about um, continuity. We can say that a function is continuous from the right of a if the right limit equals the function evaluated at that particular value, or we can say it's continuous from the left if we come from the left and that equals the function evaluated at that value. So no big surprise here. We're just saying it's continuous from the left or continuous from the right. And you might want to know this if you're looking at, let's say, something that has a domain of just a particular interval. You want to know, are you continuous all the way to the end kind of thinking, or are you not continuous at the end? I talked about this guy, the step function. Okay, so we have this guy, meaning this is the integer that is less than the, actually it is the integer, the largest integer that's less than the value, less than or equal to the value. So if we have 1.5, the integer portion here is going to be 1. So if we're looking at 0.5, then the largest integer is going to be 0. If we look at negative 0.5, the largest integer that's less than negative 0.5 is of course negative 1. So we have this kind of step ladder here. So this will be a good one to examine our definitions of these continuities. If we're coming from the right, coming from this direction, as we get closer to 1, the limiting value is 1. And so this thing is continuous from the right? Because we come this direction, and lo and behold, for each of the steps, so we can say that this whole function is continuous from the right. So long as we're coming from the right, we're going to get to whatever value n that we're evaluating. Okay? Everybody get that from the right? Now think about it from the left. If we go this way, we're still pointing to a number, but if we evaluate it at that number, so for example, if x is increasing from 0 to 1, as we're approaching 1, the limit is still 0, but f at 1 is going to be 1. And so this is discontinuous from the left. So this function here is continuous from the right, but discontinuous from the left. So you can see, from an interval what this looks like when you graph it. When you have the endpoints included, you're continuous going up to that point, but if the endpoint is not included, then you're discontinuous going, to that endpoint that's not included. So you look at this function, you say, this is not a continuous function, clearly, because there's all these steps in it. And that's true. It's not a continuous function, but it is continuous from the right. Sorry about this being so low for people in the back. Hope you can still see it. Okay, and there's my overall conclusion there. Okay, so let's move on. Another definition. So we can say a function is continuous on an interval if it's continuous on every point on that interval. Okay, so this is kind of another breakdown. If we have just an interval that we're looking at, so here we want to see that this is continuous on the interval 1 to 2. So we have to look at this in pieces here. So the first thing, let's say A is between 1 and 2. I'm not considering 1 or 2, but between 1 and 2. If we use the limit laws here, that we know that the limit as x goes to a of the square root of 1 plus x equals the square root of the limit of 1 plus x as x goes to a. And then we know that the first part, the limit of 1, is 1. and the limit as x goes to a is of x is a, so we show that this point equals this limit, and that's our definition, right? Where this, the function evaluated at a equals the limit of that function as x goes to a. So we know the interior part. So in the middle, it is continuous on both sides, right? Whether you come from the left or the right, and you can do that because you're either less than or greater than 1 and 2. So that part in the middle meets our definition of continuity. So now what we have to do is look at the limit as we go to 1 from the right? Because the function doesn't exist as x goes to 1 from the left, because I've defined my interval here, and there's nothing less than 1. But here I can do the same thing, and I can do the same thing with 2 coming from the left. So let's say this is my graph of the function, like this. If I choose any point in the middle, I'm continuous if I come from the left or the right. If I'm looking at this point, I'm continuous because I'm going only from the left, and that means that it's continuous from the left. This one I'm only coming from the right, and yes indeed we get to that value, and so we're continuous from the left. So we're continuous on every point in this interval. All right, any questions on this? So we have 4 concepts of continuity. One is just the basic definition. Number 2 is the kinds of discontinuities we have. Number 3 is the continuity from the left and right. Number 4 is continuity over an interval. Yes?
Why is that a 2 minus?
This means that it's coming from the left. Okay, so it's going up.
Okay, well,
This is the direction it's coming from, the negative side, right?
yeah. So you plug in 1 and 2 to figure out if it's continuous?
Well, here I'm doing it, the limit as this goes to 1 from the right is, basically we can evaluate that, right? Because it's always positive. And we do the same thing here, but I'm making the distinction that if I just take the regular limit at this point, it's not continuous from, this one is not continuous from the left, okay? But what I'm concerned, the thing that I'm concerned about is, am I only continuous from the right?
Okay, so if that was 1 and 3, what do you do?
Well, then I would be looking at the
That
limit
would be
as
a
this
3.
goes to 3, yeah.
Okay, that's good.
So I'm looking at how's the middle, and then how are the ends? And it's a different question because at the ends, the function doesn't exist on outside of the interval. Or at least that's not what, we're not considering that part of the function. Yes?
How would you know if it wasn't continuous?
Because one of these limits wouldn't be right, okay?
How do you know
What's
that
its,
it's
yeah,
right?
what's its right and wrong?
Oh, you want an example of one that fails?
Yeah. I don't know.
Well, let's say if this was 1 over x, and I'm looking at the interval from 0 to 1. In between 0 and 1, 1 over x is continuous. But at 0, from the right, it's not continuous. So that's not a continuous, not continuous over the interval.
Why is it not continuous? Because it's outside of the...
Yeah, because my, if I'm looking at just from 0 to 1, it's not continuous coming from this direction because it doesn't get to a value. Okay, so another example is, let's look at from -1 to 1. Okay, it's continuous at -1, it's continuous coming this direction, it's continuous at 1 coming from this direction, but in the middle, it's not continuous because you have that gap. Okay, so you have to make all three checks. Is it continuous from
Left to right.
from left and right to the endpoints and is continuous in the middle. Okay, time for another theorem.
Which word?
So these are some of those limit laws that these are derived from the limit laws. What this is saying is that if I have a continuous function and I add it to another continuous function, I end up with a continuous function. Or if I take the difference between two functions, I end up with a continuous function. Or if I multiply it by a constant, I get a continuous function. Here's the product. If I multiply the two, if I take the ratio, so long as I'm considering the fact that I'm excluding any possibility of g being 0, so I don't end up dividing by 0, you end up with continuous functions for all your basic multiplication, division, addition, and subtraction. You prove this theorem by proving that the limits exist, and you use those limit laws. And it looks very similar to the limit laws, right? Because we can take the limit of f and the limit of g, and you add those together, and you get the limit of f plus g, right? Okay, so here's some things that we can start assuming now, and these are all theorems that when you're in advanced algebra or advanced calculus or an analysis, you get to prove these things. But I'm just going to state them as theorems, and you can hopefully have a gut feel for why they're true. But these are all true, that a polynomial is continuous over all real numbers. Okay, so anything you see, 3x squared plus 2x minus 1, just assume that that's continuous. So a polynomial is continuous. A rational function is continuous on its domain. And so what's the domain of a rational function? It's everywhere where it doesn't have an asymptote, right? So all the places where the denominator gets to be a 0, it's not continuous there, but it is continuous everywhere else. So it's continuous on its domain. And root functions are continuous on their domain as well. So, we take the square root of x. The domain is x is greater than or equal to 0. We're going to assume that that's continuous over that whole domain. X is greater than or equal to 0. And with odd root functions like the cube root, negatives propagate through that, so that's continuous over all real numbers. Okay, so we're kind of building, just like we had a toolkit of functions, we're starting to build now some rules that we can apply for continuity. Okay, so one of the things that is difficult, I think, in math is that when you look at theorems, you tend to look at what the theorem is concluding. Like I showed you, the definition of a limit, and you have, the limit of something approaches the function evaluated at that. You probably forgot what that first sentence said before that, okay? We're going to have a lot of theorems that are going to say, assuming f is a continuous theorem or a continuous function, then they'll give you a property. Make sure you really note that, okay? Because there are some theorems that fail abysmally when you have a discontinuous function. They only apply when you have a continuous function. So you have to read the conditions of a theorem, and you're going to have some theorems to remember and to apply. And so the conditions of them are important, okay? Okay, and it's not a trivial assumption. Okay, so let's look at some composite functions. We kind of stuck our toe in the in this before. I guess in section 1.1 we had those some of those exercises. I recall we discussed the homework in class a bit. Here it is a little bit more formally. If f is continuous at b and the limit of g as x approaches a is b, then the limit as x approaches a of f at g at x equals f at b. Now notice here that g at x does not have to be continuous, only f at x. Yes.
No,
Oh, okay. Thought you were giving me the hat sign there. Is that a baseball signal when you throw your hat out of the dugout?
I don't know. There's like a tip of the cap, like, good job.
Yeah,
When,
something like
throwing your stuff, that's like, I don't know, you messed up or something.
Probably it's just you're really angry at the umpire,
Yeah.
right? Okay, so let's look at this. So if I break this down a little further, that the limit as x approaches a of g at f at g at x is the same as f at as x approaches a of g at x. And this is kind of that hard thing to understand, that what we're looking at is where does this end up for the value of f, not where does f at x as x approaches a end up. It's where does g at x as x approaches a ends up. Okay, here's another one. If g is continuous at a and f is continuous at g at a, okay, so this is two conditions here, then the composite is continuous at a. Okay, so let's look at this in terms of this example here, where we had f at x equals the square root of 1 plus x over the interval 1 to 2. So let's say my inner function, if I want to speak that way, is 1 plus x, okay? We know that that is continuous over all real numbers, right? And so we know then that this is continuous on 1 to 2. And then we have a root function, and is that root function continuous over the values, the possible values of g at x? Well, it is. I have one more line that I cracked in here. So now we know that if our outer function is the square root of x, we have to show that the outer function is continuous from 2 to 3, not 1 to 2, because that's the possible values of this inner function on this interval, right? So as we go from 1 to 2, we go to 2 to 3, and so that's what we're concerned about for the continuity of the square root, okay, is that interval. Okay, we're going to have two theorems that sound like they should be the same thing, but they're not. One of them is called the intermediate value theorem. The other one that we're going to talk about in a week or two is going to be the mean value theorem, and they're different. Okay, so I'll give you a clue when we talk about the mean value theorem how I remember the differences between the two, but for now, this is your first major theorem here, that suppose f is continuous on a closed interval, and let n be any number between f at a and f at b, where f at a does not equal b. So here I'm saying at a, and here I'm saying at b, okay, we have two values, and f at b and f at a are these values plotted. And if I choose any value between these two, okay, and I'm going to assume that, not assume, I'm stating that f is continuous, and this is a serious requirement of this theorem, is that if it's continuous from here to there, that there is going to be some value, c, that's between these two numbers such that f at c equals n. Okay, so that probably doesn't make much sense to you until I show you the rest of the graph. So let's say we have one possible f at x. Okay, I'm not saying what f at x is, but this is certainly continuous. So if I choose n, there is a c that's in between a and b that give me that value, f at c equals n. If I choose a different function, okay, then my c is someplace else, but it's still there. So in other words, if I have n as this value, and my function goes from here to here, I'm going to cross n, if it's continuous. And if you look at it that way, it's a little bit more, I think it's a little bit more intuitive. Okay, if my function goes from, let's say, 1 to 5, I'm going to have to cross over 4 at some place. With a continuous function, with a discontinuous function, that's possibly not true, where you just, you have a step, and that step leaves you a gap. And so a discontinuous function, this isn't true, but for a continuous function, that is true. Okay? Does that make sense? Do you get what the theorem's saying? Read it again, or I'll read it out loud again. Suppose f is continuous on the closed interval a to b, and let n be any number between f at a and f at b, where f at a and f at b aren't the same number. Then there exists some value c within this open interval. Notice this is a closed interval, and this is the open interval, so it doesn't include a or b, such that f at c equals n. All right, so what I'm saying is that when I have this situation where these are 2 points on my function, that I can choose any number in between them, and I'm going to find that there is some value in between a and b that make that work. Okay, so let's have an application of this. You know what a root is, right? It's the solution to a polynomial equation that makes it true, right? So any value. So the hard way to do this is to factor it, if it factors, and finding all the roots, and then saying is one of them between 0 and 1. That's the hard way. All I want to know is there does a root exist between 0 and 1? Okay, so let me do this. I'm going to call this equation, I'm going to make it a function, and I'm going to evaluate this function. It's continuous from 0 to 1. We know that, right? And so I'm going to say, okay, f at 0 is going to be what? It's going to be -6. That's easy to figure out. And f at 1 is going to be some positive value, 7. So if I go from -6 to 7, I have to cross 0 someplace in between 0 and 1. So I'm telling you that there is a root right there. And in fact, you can find the root or approximate it by continuing to do this by getting numbers. Okay, well, let me try between 0 and a half. Let me try between 1/4 and a half. Let's try between 3/8 and a half. You can kind of narrow down so long as you're above 0 on one side and below 0 on the other side. You can shorten that interval and get to an approximation of the root. Do it with a method called bisection, where you go halfway each time. It's kind of like guessing the number between 1 and 100. You say high, low. It's that same kind of thing. And so here, because this function is negative at 0 and positive at 1, you know that someplace f at something between 0 and 1 equals 0. Okay, so I can demonstrate the existence of a root using the intermediate value theorem. Now, one of the things I may ask you to do this is to say, show me that there's a root between 2 and 3. And I'll give you a function like this. You just can't do this. What you need to do now is you have to say, because of the intermediate value theorem, there exists a number where f at x equals, there exists a number, say c, such that f at c equals 0. Okay, so you have to actually call out the theorem as your reason for something being true. Okay? That's the simplest kind of proof that you can do. Okay, so you can say this. F at 0 is less than n, which is less than f at 1. N is 0. And so by the intermediate value theorem, there exists a number c in the interval 0 to 1 such that f at c equals 0. So this is the statement that is the answer. And so we're going to get away a little bit from providing answers that just x equals 5 or something like that. You're going to be, if the question is show that there's a root here between 0 and 1, there's several ways to do it. This is using the intermediate value theorem, and so you have to quote the intermediate value theorem. Any questions?
So it's always gonna be 0 and 1, right?
It's not always going to be 0 and 1. I can ask you, is there a value between -1 and 0?
So,
Is there a root? I mean, these are arbitrarily chosen. I'm saying, in this function, is there a root between these two numbers? And so I can choose those numbers wherever I want. The answer is either yes or no. It's not ever no. It's that it's not definitely yes. Okay. So, for example, you may have a function that looks like this. Okay, and I'm interested in the interval from here to here. So let's say this is, 10, and this is, let's say 5. I can evaluate f at 5 and I get a negative number. Here I get f at 10 and I get a negative number. I can't definitely say that there's a root, but there certainly may be. It's only the numbers in between f at 5 and f at 10 that I can guarantee that those numbers exist. And just because I can't guarantee it doesn't mean that it doesn't exist. It's just I can't guarantee it. Okay? All right, and one last little tidbit here. When you're plotting a function, by evaluating several different things, and you draw the line to connect them, you're making the assumption that's a continuous function, right? So really, it's kind of one of those assumptions that's a pretty good assumption. It doesn't take a whole lot of stretch of the imagination to make it right. Okay, but in fact, the assumption that you're making is that the function is continuous.